Good afternoon, everybody. We start lecture on medical and biological physics. It is the second one, vibrational motion and waves, physics basics, acoustics, some aspects. This is the title of today's lecture. And the goals of this lecture is to specify mechanical waves as physical factor in context of this factor, human body functional state effect. What are our objectives? They are vibrational motion and waves nomenclature and basic laws review. Human ear sound perception, physics aspects, and physics aspects of mechanical waves human body effect implemented in medical practice. This is the plan we will follow through. The first point of our plan. It is the vibrational motion and waves physics basic aspects. Processes that are repeated at the same intervals are called vibrational ones or oscillations. Mechanical vibration oscillation, when an object moves back and forth repeatedly over the same path, it is said to be oscillating or vibrating. The oscillation of a body or system with its own natural frequency and under no external influence other than the impulse that initiated the motion is said to be free oscillation. When energy is fed into vibrating system, this system is said to be undergoing forced oscillations. Here you can see two vibrating systems that are the simplest ones, may become considered as the examples, very good examples, to show how we can numerically specify mechanical oscillations. Oscillation is the kind of mechanical motion, and mechanics' task is to determine the position of the object into the space at any instant, at any moment of time of interest. So this change of the position with time is represented by the motion law, and for this simple harmonic motion, this motion law may be represented analytically by that means. You can see that it is harmonic function cos. This is the maximum displacement of an object relatively to its an average equilibrium position, and this is the change of the position into the space with the time. And you can see that this cos function repeats its magnitude, so consequently this position is changing repeatedly with time into the space of that vibrating, oscillating object. What should be mentioned here? This function of the coordinate, you remember that the position of the object is determined by three, in the general case, coordinates. But in this particular case, these two vibrating systems are moving along the only one axis, and this is x-axis that is chosen here. So consequently, the only one coordinate of the object under investigation is changing, and consequently the law of this kind of motion is represented by the only one function. X with index m is an object maximal displacement from its equilibrium position, that is oscillation amplitude. Omega is an object angular circular frequency omega equals 2 pi, pi is a constant, you remember, times frequency. Just that frequency as the number of the completed oscillation per unit time, particularly per 1 second. And this phi 0 is an object oscillation initial phase. Determining an object initial position oscillation starts from. So you can start to investigate oscillating object at any moment, and this doesn't mean that the object would be at its equilibrium and average position. It might be at any position into the space, and just this as oscillation initial phase shows what is initial position for the object you start to investigate it from. So you can see these two simple vibrating system, the weight on a spring and the simple pendulum, the massless rod with the point mass on its free end. An oscillation period is the time required to complete one full oscillation. An oscillation frequency, as it was said already, is the completed oscillations number per unit time. And now please pay your attention to this. That is of very importance. It is very important to recognize when we will analyze what is analyzed, what are characteristics that ear analyzes of the sounds, you will recognize that the number one is just the frequency. And I try to say you that the free oscillations frequency is a vibrating system own natural frequency determined by vibrating system parameters. Look, for this weight on a spring, you can see circular frequency is determined by spring coefficient and the mass attached, connected to the spring free end. So that is why, look, when we take this, the simple pendulum, you can see one more time, circular frequency is determined by the length of the massless rod and is determined by the gravitational constant at the place of the investigation of these system oscillations. So that is why, look, when you recognize this as the frequency, you can do conclusion about the vibrating system. You can recognize this system. Frequency carries information, identifies the vibrating system. So that is why, to identify the object that can't be seen by eyes, ears analyze the frequency of the vibrations developed by not seen object, and by the frequency ears identify that oscillating system, and by that means ears bring information about person's surrounding. So, and then when a frequency of an external force is equal to a vibrating system free oscillations frequency, an amplitude is largest and the system is at resonance. So you can see what is the resonance when the external force subjection frequency equals to the oscillating system natural own frequency. the amplitude of that system, vibrating system, becomes the amplitude of the oscillations becomes the largest. So let's go further. And look, there is a repeated interchange between kinetic and potential energy. Portions of a vibrating system undergoing simple harmonic motion. Vibrating system undergoing simple harmonic motion, total mechanical energy is constant when we ignore, it is understandable, the friction at the point of the attachment of the rod, and when we ignore the resistance of the air where systems are moving at. So, and this gives the possibility to express these vibrating systems' total mechanical energy, energies as the combination at any moment of kinetic and potential energies. This analytical equation shows you what is the maximum kinetic energy would be stored into vibrating system, and this is transferred in turn into the same amount of the potential energy. So, and this equation shows you that energy that is stored into vibrating system depends, is determined on the circular frequency and amplitude squared and the mass of the vibrating system. Same for the spring, for the weight on the spring, you can see the same kinetic energy is transferred into potential of the same amount, and one more time the oscillating system maximum energy depends, or it will be better to say, is determined by the angular frequency and the amplitude of oscillations. And now look, we can't ignore that vibrating systems of any kind is surrounded by the at least air that surrounds the investigator as well. Look, when we talk about this interaction between the oscillating system and the air, we can say that oscillating system to be in contact with the surrounding air, for example, or it might be another substance filling that space where a vibrating system is placed. This interaction may be considered as the disturbance of the matter. And this disturbance means the only one. Vibrating oscillating system gives the energy to the particle of the substance, of the matter, of the space. So, and then mechanical wave is the disturbances in matter that transfers energy through the matter. Mechanical waves start when matter is disturbed. A source of energy is needed to disturb matter and start a mechanical wave. The energy of a mechanical wave can travel only through matter. The medium is required. The medium is required. This diagram illustrates the production of mechanical wave in a medium by a piston that oscillates back and forth at a frequency f. When it moves forward, it compresses the medium and a compressional wave moves outward. When the piston moves backward, there is a region of reduced pressure, rarefaction. This disturbance also travels outward. You can see this disturbance by piston of the air that is into the cylinder, so that is not closed. And what is the result of this disturbance? The development of that compression and rarefaction regions that are traveling within the cylinder with this velocity. And when we make immediate photo, we can see this pressure within the cylinder change along its cylinder axis. And let's look inside the air and let's recognize the behavior of the particles of the air obtained, supplied with the energy from this vibrating system, as in this particular case, the oscillating piston. Look here. When a gas, liquid or solid is mechanically disturbed, as in this case, mechanical waves are often produced. In these waves, the molecules of the substance vibrate and collide with one another, but maintain the same average position. However, since their motion are coordinated, a wave results and energy is transmitted even though no net particle displacement occurs. Note that the individual molecules don't travel any appreciable distance, but only oscillate about their average positions. And one more time, we can write down the law of the motion for the individual particle of the air that is disturbed by vibrating system. And pay attention, this is just the amplitude of the oscillation of the particles, and it is of the order of the radius of the air particle. So that is why there is no noticeable displacement of the particle of the air. They are oscillating, they are vibrating around their initial and average positions into the space. And one more time, you can see the velocity of the propagation into the medium depends on the density of the medium and depends on this bulk volume bulk modulus. This quantity is a measure of how hard it is to compress a substance. When the pressure on an object is increased, its volume decreases. Its density, which is mass to volume ratio, increases. The bulk modulus relates the fractional density change to the pressure change. A material such air that is easy to compress has a small bulk modulus. Stiff materials such as steel have large bulk moduli. So consequently, the velocity into the gas of the mechanical wave is less than into the water, that is less than into the solid. So, and classification of the mechanical wave is based on the kind of vibration of the particles of the medium. What does this mean? The kinds of the vibrating. The direction of the vibrations of the particles relatively to the direction of the propagation of the mechanical wave. Transverse, longitudinal, and surface waves are three types of mechanical waves recognized. In transverse wave, particles of the medium vibrate up and down perpendicular to the direction of the wave. you can see this kind of the mechanical wave. In a longitudinal wave, particles of the medium vibrate back and forth parallel to the direction of the wave. And this kind is just of interest to applied staying on position of the possibility of application of the mechanical waves. Just longitudinal waves are useful to be applied for investigation. A little bit later, you'll see how it is done. In a surface wave, particles of the medium vibrate both up and down and back and forth. So they end up moving in a circle. You can see how this may be produced and what are the kind of the vibration of the particles within the surface wave. A surface wave is a wave that travels along the surface, separating two media. We talk about these two kinds that are traveling within the just media, but this kind of waves travels just along the surface, separating two media. And look, some characteristics of the wave motion, mechanical wave. So vibrating objects are sources of waves, which may be either a pulse or continuous. Wavelength is a distance between successive crests. Actually, we can say more clearly, more certainly, what is actually the wavelength? It is just the distance mechanical wave travels within one time period of particle oscillation. Each particle completes its cycle of the oscillation after time period. And within this time, energy travels to the distance that is named as the wavelength. A frequency is a number of crests that pass a given point per unit time. An amplitude is the maximum height of a crest. A wave velocity equals to this product of the wavelengths and the frequency. So you can see this process of propagation of mechanical wave. And actually, one more time, we say about the displacement of the particles of the space, of the medium, where mechanical wave is traveling, is propagating. But now there is no the only one particle that is oscillating, that is moving into the medium. But there are too many particles of the medium. So that is why we should express this situation analytically as the process of the displacement of too many particles. But we can do this individually for each particle, and it becomes to be the sinusoidal wave equation. Let me repeat one more time. What is the task? To show that the particles of the medium displace, and this depends, in case of mechanical wave, not only on time, but also on position of the particle relatively to the source, relatively to the position of vibrating system, delivering developing the mechanical wave. And when we collect this all together, you can see we obtain this wave motion equation that shows that is actually the motion law for individual particles of the medium that are at different distances from the source of mechanical waves. Any particle may be investigated and you can obtain the motion law for any particle of the medium through this wave motion equation. This collects the laws of motion of all particles of the medium, of the space where mechanical wave is traveling through. So, and after that, let me show you the examples of mechanical waves generation and registration. What is this? It is the investigation of the pulse. What is the pulse? It is the vibration, oscillation of the artery wall that is under the skin at this wrist position that is closest, and when you touch this place by endings of your fingers, you can perceive these vibrations, mechanical vibrations, and when you count how many are per 1 minute, for example, you can say about the same number of the heartbeats per minute. One more time, the voice structures produce the same as the piston disturbance of the air, and this produces the mechanical wave that may be transmitted and analyzed and taken by the ear. These are the example of natural, I may say, mechanical waves produced by the natural structures. And look, we talk about mechanical wave as about the process carrying the mechanical energy through this space, through the medium. So, and we can say that, for example, the surface, flat surface of the area meets mechanical wave. This means that it meets this amount of the energy, mechanical energy. This energy strikes that flat surface within this time. When we divide the amount of energy crossing the surface of area by time, we obtain the flow of energy or wave power. A wave intensity is the ratio of the flow of energy to a surface area, and you can see that the intensity, how much energy is carried through unit surface area per unit time, depends on medium this wave travels through, depends on amplitude of the vibrations of the medium particles, depends on circular or frequency of the vibration of the medium particles, and depends on the velocity of the propagation of the mechanical wave into the medium. You know that it was talked about this already. Velocity depends on medium density and how hard is medium compressed. The gas is the medium with the lowest velocity, 330 meters per second. The liquids are of acoustic impedance. It is the product of the density and of the medium and velocity of mechanical wave into this medium. This is an important quantity in determining how much sound is transmitted from one medium to another. When a wave meets a change in medium acoustic impedance, it splits. Some of it goes through, some is reflected back. And this depends on the mechanical impedances of the media that are separated by that striking, by the surface that mechanical wave strikes. If the impedances of the two media are very different, then much of the sound will be reflected, not transmitted at the interface. The media are said to be acoustically mismatched. For normal incidence, when this angle equals to 0 degree, reflection coefficient may be expressed by that means. And this we will come back to when we talk about that structures as the middle ear structures. The ear has to arrange for acoustic to avoid acoustic mismatching. The ear has to arrange for acoustic matching when the sound passes from air to liquid at the middle inner ear interface. And this is just the role of the audible ossicles to match acoustic impedances of the air and internal liquids inside the inner ear. So please take the example of the reflection. You know this, and now you can recognize the physics of the procedure that you name in your language. It is auscultation. So look, these rubber or plastic tubes provides the surface with the very different mechanical impedance with respect to the air that fills this tube. So consequently, the mechanical wave totally reflects from this surface and continue to propagate into this tube and reaches the ears of the investigator to be heard. And this is just the example of the total internal reflection that is implemented in medical practice, actually. And now you understand the physics of this. And one more physics effect regarding the behavior of the mechanical waves. Look, it might be that situation when the source of mechanical wave and the observer are moving relatively to one another. And when source produces the mechanical wave, this mechanical wave is detected detected by the observer to be of different frequency. Look, the frequency changes of original mechanical wave that the source or the observer are at relative movement with one another. Wavelengths and frequency of sound waves, mechanical waves, emitted by the source and are moving with the velocity into this space when there is no relative motion. Motion of the source that is moving with velocity relative to the observer alters the wavelengths and frequency of sound waves. So consequently, this is the base, one more time, for the one more diagnostic method as the method to determine the velocity of moving structures, particularly into the human's body. If this Doppler frequency shift, so original and produced frequency change will be detected, the velocity of the structure of the source of the mechanical wave may be determined. Doppler effect, the shift of original frequency of original sound, mechanical wave. And what? Look, waves frequencies range diagram. It is the principle to classify mechanical waves, to take the frequency as the characteristic of mechanical wave and separate mechanical waves into three ranges. Look, the first, it is infrasonic mechanical waves of the less than 20 Hertz frequencies, acoustic mechanical waves that are audible, that might be heard by the human's ears. The frequency ranges within these 20 Hertz and 20 kilohertz range. And ultrasonics, ultrasound, this is greater than 2 kilohertz, to 20 kilohertz. This is just one more classification of the mechanical waves. First classification, we can see that and the principle to classify mechanical waves was the relative direction of the medium particles oscillations and direction of the wave propagation. It is the first classification, and this is the classification number 2. The frequency is the principle, is the characteristic. This classification is based on that. The next, we start to deal with one more. Sound was mentioned already. But let's look, let's stop to talk about sound, and first of all, let's consider this range of the mechanical waves as ultrasonic waves or ultrasound, and how these may be implemented in medical practice. First of all, physics, how these kind of mechanical waves produced. Ultrasound can currently be produced at frequencies as high as somewhat more than 10 to the power 9 Hertz. It is widely used as diagnostic, therapeutic, and surgical tool in medicine. The ultrasound generator is a device basically consists of a sine oscillator and transducer. The sine oscillator generates high frequency more than 20,000 Hertz electric power, while the transducer unit converts the electric oscillations into mechanical ones. The electroacoustic transducers used in the ultrasound range operate on the basis of various phenomena. These as piezoelectric ultrasound generation shown at this diagram. If pressure is applied to the surface of appropriately cut plates or discs of certain monocrystals, for example quartz, electric charges are generated. This is the piezoelectric effect. The effect is reversible, that is, if electrodes are placed on the crystal plate and the potential difference is applied to the electrodes, the plate will be deformed by electric field. This is inverse piezoelectric effect. In an alternating electric field, the thickness of crystalline plate follows the vibration of the electric field. That is, the crystalline vibrates, producing ultrasound. It is shown here. The piezoelectric transducer. But we can say about same effect for magnetostrictive materials that exhibit similar behavior but in an applied magnetic field. Both types of transducers also act as a receiver, since the mechanical vibrations produce electric and magnetic fields. They can be detected and used to monitor incoming sound waves. This is the physics to produce, the physics idea to produce ultrasound. To apply electric or electric energy or energy of alternating magnetic field and transform this electromagnetic energy into the form of mechanical energy, of mechanical waves. You can see the regions of the application, ultrasound applications in medical practice. For therapeutic purposes, for example, in case of rheumatic complaints, ultrasound with a frequency of 0.8 up to 1.2 megahertz and intensity of maximum a few watt over centimeter squared is usually applied. This therapeutic effect is mainly due to mechanical pulsating effect, micro message, and heat production. The background of the diagnostic application of ultrasound is its reflection from the boundary media of different acoustic impedance and the fact that the time interval between the emission of the ultrasound and the return of its echo is proportional to the distance of the reflecting surface. This permits non-invasive insight into the structures of the tissue. The average ultrasound intensities required for the examination are of the order of magnitude of 10 milliwatts over centimeter squared, the physiological effect of which can be neglected. Ultrasonic offers a method of investigating objects internally without causing any damage. It is widely used in medicine, and this diagram illustrates what are the areas that might be ultrasonic investigation. An ultrasound beam is directed into the body. The reflections or echoes from different structures are then detected and analyzed, yielding information about their locations. There are several different modes of display. And you can see here that the motion of the object may be investigated as well. The motion of the object may be investigated as well. So, and this one more time. We repeat, the ultrasound imaging relies on the reflection, so the strength of the echo depends on intensity reflection coefficient. So any boundary with the air results in almost 100% reflection. So this means that coupling medium is needed to introduce ultrasound into the body. The sonar principle is used to estimate the depths of a structure using this formula. And the example of that investigation may be given as the A scan. The A or amplitude scan is essentially a range measuring system. The rate generator, look, at regular intervals, this simultaneously activates the transmitter, the time-base generator, the time gain compensator. Transmitter stimulates the piezoelectric transducer to emit a short microseconds sharp pulse of ultrasound into the body. Transmitter stimulates the piezoelectric transducer to emit a short microseconds sharp pulse of ultrasound into the body. The time-base generator, the time-based generator supplies a voltage across X plates, horizontal deflections of the cathode ray oscilloscope, so that the spot starts moving steadily across the screen. The time gain compensator controls the exact amplification or gain of the returning signal. This one. Receiver. A voltage is generated into the transducer probe. Voltage is generated here whenever an ultrasound pulse arrives there. This occurs both when the initial pulse is sent out and when reflected pulses return from the patient. These voltages are amplified at the receiver and applied to the Y plates of the cathode ray oscilloscope, causing a vertical deflection of the moving spot. A vertical line thus appears on the screen each time an echo returns to the probe. The positions of these lines on the screen, for instance 1, 2, 3, 4, 5, correspond to the positions of the associated reflecting surfaces in the body, that is, one body surface, second, third, fourth, and fifth. Time gain compensator. Time gain compensator. One complete movement due to attenuation of the ultrasound pulses in the body, echoes from deeper interfaces tend to be very weak. These weak signals might contain valuable information. To ensure that they are not lost, they amplified more than those originating close to the probe using time gain compensator. This increases the gain of the receiver with time at an appropriate rate, a technique known as time gain compensator. Cathode ray oscilloscope. One complete movement of the spot across the screen corresponds to the transmission of one pulse and the receipt of a number of echoes. If this entire process is repeated very rapidly, a continuous trace is seen on the screen. Such a trace is shown here. A typical A scan from a fetal head. The large peak A and B correspond to echoes from the two sides of the skull, whilst the smaller peak C is due to an echo from what is known as the midline of the brain. Using the cathode ray oscilloscope, calibrated time base estimates of time intervals between echoes may be made. For example, the time elapsing between peaks and A and B on the screen can be recorded. This corresponds to the time taken for an ultrasound pulse to travel from the near side of the baby skull to the far side and back again. Then, knowing the velocity of the pulse in the tissue, the diameter of the baby's head may be evaluated using the equation diameter equals velocity of ultrasound times time interval between A and B over 2. This distance is a good indication of the age of the developing baby and can be used to predict a delivery date. Such A-scan measurements have been widely used in routine screening of pregnant women. You can see this is just the A-scan of a fetal head about 18 weeks from conception. Static B-scan is interpreting these peaks, transforms these peaks of the deflection of the oscilloscope ray into the contrast picture of the structures. Look, this is just the technique of the simple sector B scan. The probe is rocked on the surface. You can see the coupling gel is placed on the surface to conduct, to avoid the reflection. And the picture, by that means, one more time, by reflection and storing the ultrasound energy, is reconstructing. This is the probe, is used to acquire an image of newborn baby brain. You can see this is the transducer and the method of the investigation. So the B-scan is essentially a white or black image. Strong echoes produce white areas, while echo-free regions are black. Fluid-filled structures like the gallbladder produce, as this, for example, produce large echoes from their walls, which consequently appear white. So in B, the contrast between the light appearance of the diagram and liver tumor, strong echoes, the gray liver tissue, some echoes, and the black cross-sectional of normal blood vessels, no echoes, and these all are clear here. This simple sector scan, as this you can see here, suffers from the need to have extremely skilled and experienced operators in order to get clear images. Furthermore, it provides a relatively poor quality focusing, so it has now largely disappeared from routine hospital work. However, its advantage of only requiring a small entry window or footprint makes it suitable still for particular applications, like imaging the infant brain through the fontanelle, as I show you here, for example. The space between component bones of the skull is very small, but nevertheless the ultrasound probe is good enough and used to acquire an image of newborn baby brain. And image clarity should be recognized. Resolution describes the fineness of detail observable in an image. Good resolution implies that very small structures can be distinguished. When considering an ultrasound image, there are two types of resolution: axial and lateral. Axial, or depth resolution along the axis of the beam, describes the ability of the beam to detect as separate two objects at different distances, both directly in the path of the beam. It depends on pulse duration. The shorter the pulse, the better the axial resolution. Heavy damping in the transducer leads to short pulse duration of less than 1 microsecond. This results in axial resolutions between 0.1 and 1 millimeter. If two surfaces are closer together than this, they will be seen as a single surface. Lateral resolution describes detail distinguishable at right angles to the beam. For example, will the lump AB in the top reflecting surface be detectable? Firstly, lateral resolution depends on beam width. Narrow beam give a good resolution. Secondly, high-frequency beams produce better lateral resolution due to a reduction in diffraction blow. However, high-frequency beams suffer the greatest absorption, hence a compromise is necessary between resolution and penetration, restricting the particle frequency range. Different probes are used for different frequency range, the most common range being between 3 and 10 megahertz. And so you can see physics and that recommendations for the application of the ultrasound. So, and now let's consider this as the application of the ultrasound to detect the velocities of the moving objects. This technique is based on the Doppler effect, and Doppler effect is the apparent change in frequency when there is relative motion between transmitter and receiver. Doppler system measure the Doppler shift in ultrasound frequency in the echo from moving reflectors in the body. This Doppler shift gives a value for the velocity of the moving reflector. You can see this is measured, and after this the velocity of the moving object may be taken from here, and this is just the velocity of ultrasound inside the body. This is known. Doppler shift is in the audible frequency range, monitored by ear using headphones or a spectral Doppler display on a cathode ray oscilloscope. Used to monitor the adult and fetal hearts and blood flow in vessels and abdominal structures. This is just a diagram showing you the Doppler system. All of the systems considered so far have used pulse echo techniques, relying on the range finding capability of short, sharp pulses. In contrast, Doppler systems monitor the velocities of moving structures by detecting frequency changes in reflected signals. They can therefore employ either continuous or pulsed waves. Doppler scan is often used in continuous with standard pulse echo imaging. The instruments available ranging from the simple pocket size versions giving audio outputs only to sophisticated color flow machines costing hundreds of thousands of pounds. Here you can see the continuous wave Doppler system, a simple system for measuring the velocity of body structures. The transmitter provides a continuous voltage output of constant amplitude and frequency, the latter generally being about 2-5 MHz. The transducer contains separate transmitting and receiving transducer, separate transmitting and receiving piezoelectric crystals. This is necessary when using continuous waves to avoid the inevitable confusion arising if a single crystal tries to emit and receive signals simultaneously. The receiver outputs signals containing the same frequency as the transmitter due to stationary reflectors, the Doppler shift frequency due to the moving reflectors. The demodulator mixes the output frequencies to generate Doppler shift delta F separately. The filter removes any frequencies other than delta F. The amplifier further amplifies the remaining signal. The recorder analyzer may simply be the ear using headphones or a loudspeaker, since typical Doppler shifts lie within the audible range. So, and this gives such signals on the cathode ray oscilloscope, showing the range of the velocities of the objects under investigation. Here you can see how blood velocity is spread within the vessel. You can see that at the walls the velocity is the lowest, is the lowest, and at the center of the vessel, the velocity of blood is the greatest, producing the greatest Doppler shift of the frequency, so consequently producing the greater signal here. And you can see how this is realized. First of all, the B scan of the carotid artery in the neck, particularly here, with color Doppler overlay, where the artery divides, there is some narrowing leading to unwanted reverse blood flow toward transducer, indicated in red. Transducer is indicated in red. So, ultrasound reflection from the moving blood, and by that means this Doppler shift frequency may be measured, and the velocity of the blood. And what are the deflectors here? It is a group of the red blood cells. These are just reflectors that are moving with this blood flow velocity, and reflection from this moving object causes the Doppler shift of the frequency, and by that means the velocity may be determined. The velocity of blood may be determined. So, one more time, you can see transducer sends the ultrasound, the flow of blood, erythrocytes inside reflect, and this changes the frequency. This frequency is different, and consequently the blood flow rate, may be determined by that means. And now let's consider one more kind of the mechanical waves that are audible and that are named as the sound, to distinct them from other mechanical waves that are not audible. So, sound waves are produced by vibrating objects which cause alternating phases of compression and rarefaction in the medium surrounding the object. The compressions and rarefaction spread out as a mechanical wave. The range for human hearing is approximately this 20,000 Hertz. The range of the average speaking voice is approximately, you can see how narrow is this range. And the intensity response. The human ear can comfortably respond to intensities from these. It is the threshold of the hearing, the lowest intensity that is required for the hearing, up to 1 watt over meter squared, so it 12 orders of magnitudes larger. So measurements of auditory response are somewhat subjective characteristics, but two objective characteristics have been fairly well established. As I said already, it is the threshold of hearing, is the minimum intensity that is just audible at a given frequency. The human ear is most sensitive to the frequencies near 3000 Hertz. The threshold of feeling at this high intensity, a tickling sensation is experienced when the ossicles vibrate so strongly that they strike the middle ear wall. Its largest magnitude corresponds to frequencies near 3000 Hertz. the threshold of feeling is frequency dependent as well as the threshold of hearing. It is the specificity of the human's ear, this dependence of the intensities, threshold of hearing and threshold of feeling on frequency, sound frequency. And this dependence is shown here. Sound intensity, you can see, and this is the sound frequency in logarithmic scale. And you can see how much this dependence is. For the sounds near 3000 Hz, it is the lowest, 10 to the power 12. And at right and at left of this 3000 Hz, intensity should be much greater to be heard. So the ear's response, you can see intensity level, is used here because of this enormous intensity range of the possibility of the ear to hear the sounds. It is common to measure intensities in logarithmic units or decibels. The intensity level is related to intensity by that means. This is 10 to the power minus 12, and when we divide the intensity of the sound, of particular sound, and take logarithm on base 10, we obtain the new logarithmic scale of intensity, or the intensity levels scale. That is more useful to characterize the sounds intensities. You can see there is no any order of 10. In addition, there is the only simple numbers. Very useful to use just this characteristic of the intensity as intensity level. Loudness is dependent on intensity, but is also a result of the energy transfer characteristics of the ear. Loudness increase is proportional intensity increase over initial intensity. Loudness increase is proportional to this increase of intensity over initial intensity. K here is proportionality coefficient. The ear's logarithmic response to intensity changes is an example of the Weber-Fechner law, which states that the change in the perceived property is proportional to the fractional change in the stimulus. It is common to a number of stimuli, including weight and brightness. Loudness is measured in phone and is strongly frequency dependent for a given intensity. These you can see that curves of the same loudness, the logarithmic scale of the intensity, that intensity level is taken as the scale for the loudness of the sound at frequency 1 kilohertz. You can see, if we talk about sound level, intensity level of this mechanical wave of this frequency, we say that intensity level of this 1 Hertz frequency mechanical wave equals to its loudness for only this. We take this as another intensity level that is required to make the sound of the same loudness. So this means that if you take this sound of this frequency, the intensity not 20 decibel but greater for different than 1 kilohertz frequency is required to produce the sound of the same loudness. So this is the curves of the same loudness. Loudness is measured in phone, and for the only one frequency, 1 kilohertz, the intensity level is considered as equals to the loudness of that mechanical wave. So, and now please let's look inside the human's ear to recognize structures and to recognize physics aspects of the hearing. Human ear is designed to convert weak mechanical vibrations of air into electrical pulses that can be sent to the brain. It consists of mechanical collection and amplification systems in outer and middle ear, and transducers to produce electrical potentials in nerves in inner ear. Human ear response to sound is of physics nature. It is essentially one of the resonances. The vibrations of the sound match the natural frequencies of vibration of ear structures. The outer ear is a tube of length 2.8 centimeter with one end closed. Its natural frequency for a standing wave of length 11.2 centimeter to be produced. So consequently, you can see that 3000 Hertz, 3 kilohertz is the resonant frequency, natural frequency for the air particles inside the auditory canal. So consequently, this frequency to produce the largest amplitudes of the vibrations of the air particles inside of the air into the auditory canal. So that is why it is understandable now why the 3000 Hertz is the best to be heard, because of the resonance where inside the auditory canal, meaning the particles of the air that fill that canal, that become to be in resonance with this frequency as 3000 Hertz. And let's look more detail to complete this consideration of the physics of sound perception. Into the outer ear. The external auditory canal, air vibration is passed to the tympanic membrane, which is paper thin, look, 0.1 millimeter, with an area of about 65 millimeters squared. The tympanic membrane fibrous structure is of K elasticity coefficient. It is relatively strong, but can be ruptured by loud sounds. Periodic oscillations of air molecules of the frequency omega equals 2 pi f produces acoustic pressure on tympanic membrane. The magnitude of this acoustic pressure changes with time, and the maximum pressure is determined by the intensity of the sound and acoustic impedance of the medium. It might be, for example, water when you are swimming, or it might be the air at normal condition. The maximum force, consequently, on the tympanic membrane may be calculated by that means. When we talk about the tympanic membrane, this may be considered as the elastic object, and we can apply the Hooke's law, and consequently we can say about the amplitude of the deflection, the amplitude of the deformation in our case of the tympanic membrane. And you can see the amplitude, the maximum displacement of the tympanic membrane is directly proportional to the intensity. And it is inversely proportional to the elasticity coefficient, and this is regulated and protect from the rupture of the tympanic membrane by the muscles that are attached to the opposite ends of the tympanic membranes. So when muscles contract, they increase the elasticity coefficient, and this decreases the displacement and prevent the rupture of the tympanic membrane. So the middle ear ossicles act as a combination of lever and pistons, which with a mechanical advantage equals to this product of the coefficients. What should be mentioned else is the eardrum and the oval window areas ratio is around, look, 20. And the resultant pressure increase to the oval window is of the factor as this product. It is around 36 times. It is of around 36 times. When sound is transmitted into a different medium, a proportion of the sound is reflected depending on a property of a medium called the impedance. If the impedance is similar or matched, then this avoids the loss of energy by reflection. The middle ear is designed to produce good matching. So, and moreover, it plays the role of the amplifier of the sound to transmit it into the inner ear filled with the fluid. The inner ear, this where things get rather complicated. The inner ear is a cavity deep within the skull which contains two organs. The semilunar canals are narrow fluid-filled tubes which are not for hearing but for sense of balance and body movement. The cochlea is also fluid-filled tube, and this is shown just here at this slide. Of 3 chambers, coiled and about the size of the little fingernail. If it were uncoiled, the tube would be about 3 centimeters long. The pressure wave from the oval window passes through fluid called perilymph down the spiral into vestibular chamber. The pressure variations absorbed at the return end by the round window membrane. Between these chambers is the cochlear duct or medium chamber filled with the endolymph fluid. This contains the sensors in which pressure waves generate electrical signals. This is a complex process which is not fully understood, involving the hair-like structures of the organ of Corti, which is attached to two membranes running the length of the spiral. Cochlear organ. The basilar membrane consists of fibers which are short, around 0.04 millimeter, and tense at the base near the oval window, increasing in size up to 0.5 millimeter and becoming slacker at the narrow end. As the pressure wave travels along the chambers from the oval to the round windows, it sets the basilar membrane into vibration if the frequency is greater than 20 Hz. This movement is transmitted to hair cells, which brush against the tectorial membrane. The liquids on either side of these membranes, the perilymph and endolymph, have different ionic compositions, which results in a potential difference across the membrane of about 150 millivolts. The sharing action of the hair cells and their interaction with the membrane changes this electrical potential and causes a current to flow in the nerve fibers at the base of the hair cells, which is transmitted as information to the brain. Within the inner ear, the pressure variation becomes a traveling within the fluid. The amplitude of the wave decays as it travels, and this depends on the frequency of the wave. High frequencies are absorbed in a short distance, low frequencies in a longer distance. This causes different parts of the basilar membrane to be affected by particular frequencies. Thus, the short fibers of the organ of Corti near the oval window respond to high frequencies, while the longer fibers at the narrow end detect the low frequencies. Below 20 Hz, there is no stimulation of the hairs. So, and after this, the signals from the hair cells that conduct their potentials to the endings of the auditory nerve, then these signals are sent into the brain. The brain discriminates frequencies by distinguishing the places from which the impulses come. The combination of these various resonances gives the ear its frequency range. the high frequency limit is about 20 kilohertz through these falls with age. So you can see how inner ear is analyzing the sounds on their frequencies, and this as frequency gives the information about the source of that or another sound. And these different sounds of different frequencies are separated into this space on the surface of the basilar membrane. It is just the idea of the inner ear analysis of the sounds on their frequencies. And after that, this is completed by recognition of that particular frequencies into the brain, by the brain, where the sounds of different frequencies are recognized as coming from different places at basilar membrane. This is the idea to separate sounds and on their frequencies and recognize the vibrating systems. And finally, several words about diagnostic procedure as pure tone audiometry to recognize the dependence of the threshold of hearing of persons to do conclusion about the hearing condition, about the ear functional state. The purpose of pure tone audiometry is to determine hearing threshold levels for pure tones. What does this mean, pure tones? It is the set of mechanical waves of the single, of the only one frequency. The pure tone audiometer is designed in terms of a set of basic functions. Sinusoidal signals, pure tones at standard frequencies is produced and through the headphones are delivered to the human's ear. And the audiogram as the hearing level in decibels dependent on frequency is restored, and by that means using this special paper the state functional condition of each ear is obtained and after that may be analyzed. So then summary. Physics methods as ultrasonic scanning and audiometry are objective, evidence-based diagnostics of human body structures condition. Physics processes involving the structures of the outer and middle ear provide conduction and increase the sound intensity of the frequency range that is audible and intensity that is required to be heard, followed by the development of the auditory sensation. Physics processes provides that development of auditory sensation. The physics theory is evidence-based in terms of the feasibility and necessity of analyzing sounds by frequency as a parameter that uniquely identifies sound sources. We recognize why the frequency is identifying parameter to recognize the vibrating system. So, and look, this is just the resources for you to add and to write the range of the information you obtain now. So, time of our lecture is over. Thank everybody. Meet you next week when we continue with the third lecture. Let's now continue with the tutorials, and let me announce the tutorial for group 102B. Please, now we start the tutorial, and don't worry if it would be a very short delay, because I need to exchange the place, my working place, and this might require more than 10 minutes. So, and we start not later at 2 p.m. Thank you for understanding. We finish.